Hi, Physics 2. This is Mr. Janowski. This is Chapter 36, Homework 2, Problem 7. So we've got wires 1, 2, and 3. They're arranged at the corners of an equilateral triangle with sides of 3 centimeters. All the wires carry 5.55 amps out of the page. So if we're looking at our triangle over here we're looking at arrow points, which means these currents are all coming towards us. So we got a couple of things to figure out. So where's my pen? Here's my pen. Step 1. So what is the magnitude and direction of the total magnetic field along wire 1? So total magnetic field, I'm going to write that as sigma B is equal to question mark. The units of that will be Teslas, and we also want to know the direction. And then for part B, what is the magnitude and direction of the force on a 4 centimeter length of wire 1? Okay, so we want to know call it F sub 1, force on 1, is equal to question mark, what are the units of force? They're newtons, of course, and we also want the direction. So how do we do this? So let's pick a nice color. All right, so first let's figure out the magnetic field at wire 1 that is being caused by wire 2. So we're going to write that as B of 2 to 1. So the magnetic field caused by wire 2 on wire 1 is what that means. And our formula for that, mu sub naught times I, let's call it I sub 2, since we're dealing with wire 2, all divided by 2 pi r, and call it r2. So yeah, that's the radius. The radius here, it's the distance from 2 to 1. All right, so we'll put in our numbers, and we'll get, let's see, 4 pi. Hurry up, times 10. Sorry, I've already written it, and my computer's getting laggy. Times 10 to the minus 7th. And the units for this are Tesla meters per amp. Times I2, so what's the current? Well, all of these currents are 5 points. This is really hard to do when the computer slows down. The computer's about 8 years old. I really need a new one. So that's I, and this is divided by 2 pi, and the distance, it's 3 centimeters, which I'm going to write as 0.0300, just for good measure, meters. All right. You could also write that as 3.00 times 10 to the minus 2 is another way to write 3 centimeters, but that's how I wrote it. So plug all that into the calculator, and you're going to get B caused by wire 2 on wire 1 is equal to 37.0 times 10 to the minus 6, so microteslas, a really, really tiny magnetic field. So now we know the magnitude of the contribution of wire 2, and what's the direction going to be? So the direction is going to get a little bit complicated here. So let me scroll down and get some more room here. So, well, let me scroll back up. Sorry. So look at wire 2. It's coming towards you. So we've got to do the right-hand rule, the grip rule. So point your thumb towards you and try to think of where the magnetic field is going to be, what direction it's going to be up here. So actually, I should just try to do it here. It'll get a little messy. All right, so let's continue this line out to here. Yeah, so grip rule, your fingers, if you're pointing your thumb towards you down here, your fingers up here should be pointing over in this direction. So that's approximately the direction we've got, B of 2 and 1. But what actually are we going to call that? So let's draw in. I think it's very messy here real quick. So x-axis, and that was our y-axis. So this is an equilateral triangle. So we know that this is 60 degrees down here, which means that this is 60 degrees. Hurry up, computer. Oh, this is aggravating. So that's 60 degrees, which makes this guy here 30 degrees. Maybe I can just squeeze that in. And from, maybe I should restart my computer. Oh, well. All right, from here, so this line here to here is a right angle. So that makes this 60 degrees. And then finally, this angle down here would be 30 degrees. So all alternate interior angles down here, complementary angles, and complementary angles over there. So that's how we figured all that out. So we know the magnitude. Now we've got to get the direction. So what I'm going to do is do a step 0 on that magnetic field there. So what's that going to look like? Do I have enough room? Let's see. So again, this is a step 0. This is not a drawing of what's actually happening. Yeah, this is trying to figure out the components of things. So here is B21. So that's going up and to the left. So that must mean, and this is 60 degrees in here. So this guy has 2 components. So he's got a component going this way. Call this B2Y and call this one here B2, actually, I'm sorry. Call this one B2Y, call this one B2X. All right, so we've got to figure out what these components are. So that means we've got to do a little bit of trig. So what's our trig going to look like? So if we're dealing with this angle, so this here is a right angle. So this side here would be the opposite. This side would be the hypotenuse. What trig function does opposite and hypotenuse? That would be sine. So sine of theta is O over H. O in this case is the opposite, is B2X, and H is B2 to 1, just to be consistent how we're naming this. So what this means is that B2X is going to be equal to B21 times sine theta. So that's going to be 37.0 microtesla. I can do that better. Microtesla times sine of 60 degrees. And we're going to end up with B2X, that's an X. Plug that in the calculator and you get 32.04, so I'm keeping an extra sig fig there, microtesla. And if we look at that, that is going in the negative direction. So really what that is minus 32.04 microtesla I hat. So that's part of what we need. So maybe if you go back to this picture, you can convince yourself real quickly that B2y is going to be equal to B2 on 1 times cosine of theta. So that's going to be 37.0 microtesla times cosine of 60 degrees. So B2y is going to end up being, let me find my answer there, 18.50 microtesla. And if we look at that, that is going up. That's going in the positive y direction. So what that really means is B2y is 18.50 microtesla j hat. So that's the positive y direction. So we've got parts of our answers there, which means if we put the whole thing together and we write the whole thing in unit vector notation, we're going to get B2 on 1 is equal to minus 32.04 microtesla I hat. I need more room. I'll make it work. Plus 18.50 microtesla j hat. So that's our x and y components together. So that's part of what we need. So shouldn't take too much effort to convince yourself that wire 3 being the same distance away and carrying the same amount of current is going to cause the same amount of magnetic field at that point. So what does that mean? That means B of 3 on 1 is also equal to 37.0 microtesla. But we've got to figure out the direction. So what do we have here? So here's where 1 was. Here is where 3 was. So do your right-hand rule, and you'll find that this guy is out in this direction. So here's the direction of B 3 on 1. And what direction is that? So these guys here are my new x and y's. So this was 60 degrees here, which means this is 60 degrees here, which means from here to here is a right angle. So there's a right angle, which means this guy right here is 30 degrees. So now I've got to do a step 0 on this guy, B3 on 1. So let me get a new x and y axis. I've got this guy going down like this. This here, hurry up computer. This here is 30 degrees. B3 on 1, this is something we know. This is 37.0 microtesla. So this guy has two components. This guy has a component going this way in the negative x direction. So call that B3x, and it's got a component going down this way. We're going to call it B3y. So we've got to do the same kind of thing and figure out what these components are. So if this angle here is 30, this side, the y side, is going to be the sine one. So what does that mean? You're going to end up with B3y is equal to B3 on 1 sine of 30 degrees, which, what did that end up being? Sorry, I'm lost on my page a little bit. Okay. This ended up being 18.50 microtesla. And what direction is this? This is the y component. This one's going down. So this is going to end up being minus j hat is the direction for this one, because this is going in the y direction and it's going down. So B3y is this. If we try to figure out B3x, that's going to be equal to B31 times cosine of 30 degrees. And doing that is going to give you, it's going to be a similar number, 32.04 microtesla. And what direction is this? This is going to the left. So this is actually minus I hat, is that one there. So B3x is that. Whoop. So we have all that. So if we put it all together, I've already written it. I'm just waiting for the computer to catch up. Okay. B3 on 1 is equal to our x component plus our y component. So minus 32.04 microtesla I hat minus 18.50 microtesla j hat. So now I have the two magnetic fields that we've got to add together. This guy here plus this guy up here. So how are we going to do that? See if I can squeeze this all in at once. Change colors again. Let's go to purple. Nice purple. Okay, so that means sigma b, the sum of these two guys. Might as well call them vectors. Which is b2 on 1 plus b3 on 1 is going to be equal to, first I'm going to write b2 on 1. So minus 32.04 microtesla I hat plus 18.50 microtesla j hat. And then I have to add the other guy. So when you're adding these guys, so now I'm adding B3 of 1, this guy right here, you just add them right underneath. So minus 32.04 microtesla I hat minus 18.50 microtesla j hat. So when I add these guys together, I end up with minus 64.08, keeping an extra digit here, microtesla I hat, and the j hat components just cancel each other out. So these guys are all gone. So what that means is the sum of these magnetic fields, this is actually our answer to part A, is this, minus 64.08 microtesla I hat, which is another way of saying minus 64.08 microtesla left. I'm sorry, not minus. Let me make this an arrow. So this is really equal to, that's the worst arrow I've ever drawn. Okay. Boop. So this is equal to 64.08 microtesla left. All right. So that was a lot of work for just part A. Hopefully part B will go a little bit quicker. So now we've got to figure out the force. So we know, let's go back up to the sketch here. So we're talking about wire 1. We know that this guy has got a magnetic field going straight this way of 64.08 microtesla. So we need to figure out the force and the direction. So let's just deal with the direction real quick. So this is going to be the cross product rule. So your thumb represents the direction of the current, which is coming towards us. So you should be pointing your thumb towards you. And the magnetic field is going to the left. So hold your right hand out in front of you. So your thumb is going towards you and your fingers are pointing to the left. Now, which way is your palm pointing? Your palm is going to be pointing down. So our force in this case, I'm going to do that. Our force in this case, I'll do orange, is going to end up being down. Wouldn't it be so hard to draw a down arrow, but it is. So our force is going to be down, and how can we get the magnitude of this force? Well, this is fairly easy. This is just our formula for the force on a length of wire in a magnetic field. So this is equal to I L B sine theta, where theta is the angle between the length of wire you're talking about, which is coming towards us, and the magnetic field, which is going to the left, which those guys are perpendicular. So that's going to end up being 90 degrees. So F is equal to I. What is our value for I? Our current is 5.55 amps. The length of this thing, the length we're worried about, is 4 centimeters. So 0.0400 meters times the magnetic field, which is what we just figured out. And the magnetic field is 64.08 microtesla, so times 10 to the minus 6 Tesla. I'm writing it out this way because we're going to put it in our calculator, times the sine of the angle, and we just determined that that angle is actually 90 degrees. So if you do all of this in the calculator, you're going to end up with 14.2 times 10 to the minus 6. So micro, and the units are newtons. So there is our force. And what direction is this? We figured out that this is going down. So it seems like this video has gotten a little bit long. Hopefully it's not too bad. And hopefully that made sense.